So let us proceed and we will go for the second consequence. Okay. So what is this second consequence? Listen. Let us take, like we considered just like the last example, there will be two paths, right? What are the two paths? Like from 1 to 2, again from 2 to 1, this will be path B, okay? Or else I can travel through 2 to 1 through path C, okay? So let me take this as a cycle, okay? So you could see that it is also constituting a, what I could say, a closed cycle, okay? So if it is a closed cycle, then again by applying that thermodynamics, first law of thermodynamics for a cycle, what I can do, very simple, just you can start it from here, okay, from this point, and or else you can start it from this point, whatever the path you want. If I start from this point to this point, the arrow mark was in opposite direction, right? The arrow mark was in opposite direction, so I need to take minus, negative of, and when I am going in this path, okay, when I am going in this path 1 to 2, okay, when I am going in this path 1 to 2, the heat transfer which is happening, why I am mentioning with d dash, I can mention with d dash or I can mention with delta, okay, the only thing is I should not use d, okay, because it is an inexact differential, okay, so d dash of this path which is 1b 2, okay. Now, so from here I reached this point. Now from 2 to 1 again, so 2 to 1 again, the arrow mark and the way in which I am traveling, both of them are same, okay, the direction is same, so plus d dash q, okay, of 2 to 1 to C1, okay, which is going to be equal to, you know that summation of heat transfer will be equal to summation of work transfer, right? So again, now talk about work transfer from here to here, okay, again the direction was in opposite direction, so minus, okay, minus d dash w 1 v 2, okay. Now from 2 to 1 along this path, along this red color, and the direction of arrow mark and the direction in which I am traveling, I am applying the first law is also same, so plus d dash w, okay, 2c1, okay. Now let me do some small rearrangement. What I will do, I will take this all this 2c1 process to one side, okay, so let this d dash q 2c1 be here, and I will bring this d dash w this side, okay, so minus of d dash w 2c1, that's going to be equal to, and I will take this that side, okay, so d dash q 1b2 minus d dash w 1b2. Now listen carefully, this is an important equation, because from this only we are going to get one important form of a first law of thermodynamics. What is that? See, the difference in, okay, the difference in heat transfer and work transfer for path B, for path C, okay, so this left hand side indicates difference in heat transfer and work transfer for path C, okay, and this indicates difference in heat transfer and work transfer path for path B. We know that individually if the process happens from 2 to 1 through path B, d dash q, I will get some d dash q, okay, or else let me write it, d dash q of 2b1, that is not going to be equal to d dash q of what, 2c1, okay, that is why it is a path function, it depends on the path. As the path is varying, the heat transfer during that process will also vary. Similarly, we know d dash w of 2b1 is not equal to d dash w of 2c1. Why? This is also the same thing, because work is a path function, so if I change the path, work will also vary. But from this particular equation, what I am getting, the difference, okay, so you could see difference between this two, d dash q 2b1 minus d dash w 2b1, okay, so that is our left hand side, which is nothing but difference of heat transfer and work transfer through path B, okay, and similarly difference of q and w, okay, difference of d dash q and d dash w through path C, those differences are same, okay, so you could relate it, even though individually they are not same, even though individually heat transfer are not same, work transfer are not same. Why? Because they are not a property, Okay, they are not a property, they are path function. Okay, they will vary based on path. But if I find a difference of this two, okay, if I find difference of this two, that is d dash q minus d dash w, which is nothing but difference of heat transfer and work transfer, is same for both path B and C. Okay, this is what we are getting by this small derivation. Okay, obviously the derivations are all not at all important. The thing is the outcome. What is the outcome? Listen carefully. So we got this. Okay, d dash q minus d dash w is same for both the path B and C. Okay, I'm just doing a process from 2 to 1 through path B and through path C. Even though if I am having a different path also, the difference between heat transfer and work transfer is not varying. It is same. So what I can conclude from this? Come on, recollect it. Recollect everything whatever we discussed until now. It's very simple. This value, the difference, is not changing with respect to path, which means it is a point function. It will vary only based on the point. Even though if I have n number of paths also, the difference between them is not going to vary. Okay, because they are a point function, they will vary only based on the point, which is nothing but they are property. And what are the significance of property? We already know property is nothing but exact differential. It is a point function, it doesn't depend on the path. Okay, so how I am saying that it is a property? Very simple. Even though if I vary the path, the difference of this two is not varying, which means it doesn't depend on path, it depends on point. If it is going to depend on point, so obviously it is a property, and that we will call it as energy. Okay, so what is the second consequence? Energy is a property. In bracket you can write it is a point function, and we already know property means it has to be point function, it has to be exact differential, all those things we already know. Okay, so energy is a property. Heat and work, heat transfer and work transfer, individually they are not property, but difference of them is a property, and that is what I am going to call it as energy. Okay, and that energy is a property. To be more precise, it is stored form of energy. Just wait for a moment. Okay, just wait for 1 minute. Okay, I will say now. So the difference between this heat transfer or work transfer, that is d dash q minus d dash w, is going to give me the change in the energy. Okay, that is dE. Why I am using d here? Why I am not using d dash? Because it is stating that it is exact differential. It is not inexact differential. Okay, it is an exact differential. This dE indicates change in energy. This d dash w indicates small work done. This d dash q indicates small heat transfer. If I integrate it, I will be getting the full heat transfer. If I integrate it, I will be getting the full work transfer. And if I don't need to integrate it. This dE is nothing but what? E2 minus E1. That is, it's a point function, right? So which is nothing but the difference of final state and initial state. Okay, in this case it is E1 is final state, E2 is initial state, but I am writing it generally. Okay, so let me write it like this: final minus initial. So it's a point function. So dE can be written like EF minus EI. Okay, now so further this equation can be modified and it can be written as, I will take this d dash w that side. Okay, so what happens? D dash q is equal to d dash w plus dE. Okay, so this is the first law of thermodynamics for a process. Okay, first law of thermodynamics for a process. Of course, we are taking a closed system. Okay, we are doing it for a closed system. Okay, so this is first law of thermodynamics for a process. And what type of process it is? It is necessary the process to be reversible? No, there is no necessary, because until now I didn't take any assumption. Okay, which means this can be applied for both reversible and irreversible process. Wait for a moment, I will be talking about this equation more. Okay, so I will be talking about this equation more. Let me erase it and then I will talk about that more. So right, I said that this equation corresponds to first law of thermodynamics for a process, right? And also I said that it is for both reversible and irreversible process. Now listen, there is no assumption, okay, there is no assumption. I can use this for reversible, irreversible, everything. Now we will understand this particular equation in somewhat more detailed manner. Okay. For example, consider that I am having some, this is my system, okay, just imagine that a piston cylinder, okay, this is my system. And if you consider energies, okay, if you consider energies, generally we can divide it into two different forms of energies. Okay, one is dynamic, okay, dynamic form or energies in transit. Okay, the most popular word was energies in transit, and obviously we know that dynamics means motion. Okay, now another form of energy is static form, okay, which is nothing but stored form of energy, okay, stored energies. Okay, right. Now regarding this stored energy or static form of energy, I will be discussing in detail, okay, but I will be just giving you a glimpse. Okay, this stored form of energy is nothing but E. Okay, that is what we got now. This E corresponds to stored form of energy. dE corresponds to change in that. E corresponds to stored form of energy, and now we got that it is a property. It is a property. It is a point function. It is a state function. So what is this dynamic form and energies in transit means? It means that when some process is happening, okay, when some process is happening, that time only this energy will have meaning. Okay, other than that, that energy won't have meaning. If some process is happening, the state was changing from 1 to 2. During this process, some amount of energies interaction will happen. Okay, and that is dynamic form or energies in transit. And we talked about this earlier also. And they are nothing but heat and work. Okay, so heat transfer, work transfer has a meaning only when process is happening. So now let us consider this. Okay, let us consider some system. Okay, now it is at state 1. Okay, it is at state 1, and at state 1 this system is going to possess some form of energy, right? That is what stored energy is. What are all that? What are all that? Just wait for a moment, just wait for some 2-3 minutes, I will be talking about that. Okay, just wait for some 5 minutes, I will talk about that. When at system 1, when the system is at state 1, this system is going to possess some different forms of energies, kinetic energy, potential energy. There are different forms of energy, we will talk about that. Okay, the energy which is possessed by the system at state 1, okay, so that I will take it as E1. Okay, that I will take it as E1. So this is the energy, stored form of energy. When system is at state 1, this is the energy which is stored in it, okay, which is stored in it. Now when I am doing some process, for example I am supplying some heat, okay, let us consider I am supplying some heat Q12. Okay, I am just doing a process such that I am supplying heat, the state is changing. For example, this piston is getting what is that? The piston is getting expanded and it is reaching here. Okay, let us take it is reaching here, and this is going to be my second state. Okay, my second state, that is boundary is expanded like this. I'm just giving you an example. Okay, so when I'm supplying some heat, what is going to happen? The piston is moving up, right? The piston is moving up, which means the piston is displacing this air upward, which is nothing but some work. Okay, some work is done by this piston on the air, or we can say that work done by the system on air. Okay, now listen, I am supplying this much amount of energy into it, okay, and outcome is this lifting of work. For example, I am supplying some 100 kilojoule of heat. I am getting some 70 kilojoule of work. For example, I am giving you. Then where does that 30 kilojoule goes? That is the question. So these two are dynamic form of energies. When a process is happening, I am supplying 100 kilojoule. I am getting 70 kilojoule as a work, which is nothing but I am moving this piston, and that work corresponding to 70 kilojoule. Okay, listen carefully. I'm supplying 100, I'm getting 70 as a motion of piston. Then where does that 30 goes? That 30 kilojoule will be stored in the system itself. It will be stored in the system itself, which means the stored initially at state 1. Okay, initially at state 1 the stored energy will be E1, right? Now it will be increased to E2. Okay, and this increase in energy, okay, this increase in stored form of energy will be nothing but 100 minus 70, that is going to be 30. And this is exactly what first law of thermodynamics for a process is saying. Simple energy conservation. If you think about this, it is a simple energy conservation. Okay, I am sending some energy, okay, I am getting some energy. Those two are energies in transit. When I am doing process, that energies will have some meaning. Once after the process get over, they doesn't have meaning. So I am sending 100 and I am getting 70. Where does the 30 goes? The 30 is going to get stored in the system, and that is nothing but the change in this particular energy, okay, stored energy. Okay, so now I hope you would have understood. Okay, if a process is happening, I am supplying some heat into it, some energy into it. Some will be converted into work. Okay, some will be stored in the body itself. In which form it will be stored? We will see that. Okay, there are different forms of the stored energy. Okay, we will see about that. Okay, now I hope you would have got a very good idea about this particular equation. Okay, and this particular equation is applicable only for a process, closed system, that too. Okay, and reversible and irreversible process for both. Now I can further reduce this. Okay, I can further reduce it. How I can reduce it? Very simple. In place of dW, if you substitute PdV, okay, in place of dW, if I substitute PdV, what will happen? Sorry, this is D. I have to be careful about that. E is D. Okay, so when you are using E, you need to use D only. Okay, like inexact will be mentioned with D dash, exact differential will be mentioned with D. Okay, so what about this equation? What I did here, in place of D dash W, I substituted PdV. And where does this is applicable? Very simple. It is also applicable to process. Okay, that is fine, because this is first law of thermodynamics for a process. But where? It is applicable only to closed system. Okay, it is applicable only to closed system, and moreover only to reversible process. Why it is only to reversible process? Why it is only to reversible process? Because d dash w is equal to PdV. It is a PdV equation, displacement work or closed system work. It is defined for reversible process, which we discussed earlier at the starting of this particular chapter. Okay, so d dash w is equal to PdV. Okay, what are all the assumptions of this particular equation? 1, it has to be reversible. The process has to be reversible. 2, closed system. And 3, obviously the energy should, that is the work should cross the boundaries. Okay, so this is also first law of thermodynamics for a process, but this can be applied to both reversible and irreversible. Okay, this is also first law of thermodynamics for a process, but it can be applied only to closed system which is undergoing reversible process. That's it. Okay, now what we will do, we will talk about this energy, okay, regarding this stored energy more. Okay, like regarding that stored energy more. Now you might have got some doubt here. What is the doubt? Like this first law of thermodynamics is giving, not a doubt, it's like something which I need to say. Okay, this first law of thermodynamics is giving me change in the energy, but if I want to find out individual energy, that is energy at state 1 or energy at state 2, then what I need to do? Actually, that is not we are concerned of. So that is the beauty of first law. Okay, first law is giving us directly what we need. What actually we need? We doesn't need what is the energy at state 1, what is the energy at state 2. We need how much energy is added. Very simple. I'm supplying 100 joule, I'm getting 70 kilojoule. I'm supplying 100 kilojoule, I'm getting 70 kilojoule. The 30 will be get added into it. That 30 is nothing but change in the energy. I am concerned about that 30 only, how much the change has happened. I'm not at all worried about what is E1, what is E2. Okay, so generally what we will do in case of thermodynamics, mostly we will be concerned in finding out the changes in the energy, changes in property like that, changes in internal energy, changes in enthalpy, all those things. So some value, okay, for example E1, okay, that will be kept as our reference. That reference value, like we will be keeping it as a reference, and with respect to that reference we can find out the difference. Okay, so what I was supposed to say here, in thermodynamics we are more concerned about the difference only, we are not concerned about the individual energies. And first law of thermodynamics is directly giving us, okay, first law of thermodynamics of process is directly giving us the change in energy. What is it? Nothing but the difference between the heat transfer and work transfer in a process. Okay, so when we are discussing about second consequence of first law of thermodynamics, we got introduced into a new term called as energy. Okay, a new term called as energy, right? E. We already know that this energy is nothing but stored form of energy in the system. Okay, in the system, stored form of energy is nothing but E. And if you see the stored form of energy, generally they can be classified into two different types. Okay, one is microscopic form. Okay, first let me write macroscopic. So one is macroscopic form and another one is microscopic form of energies. Okay, so I am talking about stored energy. We already discussed about energies in transit, that is dynamic energy. They are heat and work. Okay, now so this macroscopic, first let us focus on this macroscopic form of energies. What are all the macroscopic form of energy? Just think about it. Okay, just think about a vehicle, okay, a bus, okay, which contains some good number of passengers inside. When the bus is going to move, okay, suppose there was a slope here, like a hill or something. Okay, bus is climbing over it. Okay, so initially the bus will have some velocity. Once it is climbing, the velocity will change, right? As a whole, okay, as a whole, this bus velocity will change. Okay, now as a whole, corresponding to this velocity change, okay, there will be kinetic energy changes. Okay, or I could say that this corresponding to this velocity, the energy associated with this velocity is kinetic energy. Okay, basic mechanics, right? So, but as a whole, if I consider the bus, similarly, the bus is climbing, so that there is going to be change in the vertical distance also, and this constitute potential energy. Okay, so kinetic energy is energy which is corresponding to velocity. Potential energy is due to the change in the height. Okay, so energy associated with the height. Similarly, okay, the energies, if I am going to consider it as a whole, okay, as a whole, I will be calling it as macroscopic energy. Okay, that will be macroscopic energy. Now, some other forms of energy which you could think about is the energy which is due to surface tension, okay, and electrical, okay, magnetic field, energy due to magnetic field. Okay, those will be included in macroscopic. But if you see with respect to thermodynamics, okay, these are not significant, they are insignificant in thermodynamics. So in thermodynamics, majorly we will talk about kinetic and potential energies. Okay, but think about a closed system. Okay, think about a closed system. For example, a piston cylinder arrangement. Okay, initially this is my system. Okay, okay, this is my system, and I'm doing some process. The piston moved up. Okay, this is going to be my the next step. Okay, that is the next state. Okay, so the process is happening from 1 to 2. How much is the change in kinetic energy, or how much is the change in potential energy which you could observe here as a whole macroscopically? If you see it as a whole, as a system, like it is just getting lifted, but due to this lift, as a whole, this cylinder is not moving anywhere, or else this is not going up or this is not coming down. So as you could see that the change in potential energy or change in kinetic energy was very negligible. In fact, it is not all there. There is not much change in kinetic energy and potential energy if you consider a closed system. Of course, in open system it will be there. Okay, when it comes to open system, we have to include this kinetic energy and potential energy. For example, consider flow of fluid through a turbine. Okay, so when the fluid is entering, it will have some velocity. When it is leaving, it will have some velocity. So like when the velocity at which it is entering and the velocity at which it is leaving is not going to be same, and that difference will give me the change in kinetic energy. Okay, similarly, maybe the entrance will be kept at some place, exit of turbine will be kept at some place. So entrance will have some height and the exit will have some height. So due to this difference in that, there is going to be potential energy, changes in the potential energy. So in open system, the macroscopic form of energies, that is potential energy and kinetic energy, will be included. But in closed system, as you could see, just consider a system, closed system, the piston is moving up, the piston is moving down, but the changes in velocity or changes in the position of the system is not at all going to vary. Okay, so for a closed system, okay, change in kinetic energy and change in potential energy will be negligible. Okay, will be completely negligible. Now, so macroscopic, what are the energies which we got? We have some other forms of energy, but in thermodynamics they are not very significant. So in macroscopic energy, we got kinetic energy and potential energy. Now, in addition to that, microscopic, we have internal energies. So what is meant by this internal energy? Internal energy is nothing but sum of all microscopic form of energies in a system. If you take a system, if you are able to find out summation of whatever may be, any microscopic, any molecular, okay, any molecular form of energy, any microscopic form of energy. Okay, so energy which is associated with all the energies which is associated with molecules, okay, with molecules of a system, they are internal energy. So U, I will give you a brief idea about it. Okay, so this U is internal energy. Okay, from the name it says internal energy. So the energy which is associated with molecules, microscopic level. Okay, so here kinetic energy, potential energy will be taken as a whole system, like as I said, as a bus. Okay, so there will be change in kinetic energy, there will be change in potential energy, all those things. But for a closed system, obviously kinetic energy and potential energy changes will be negligible. Okay, changes, that is very important. Changes are negligible. Okay. Now, what is this internal energy? Any form of molecular energy, okay, which is present in a system is called as internal energy. And what are all those? Like I already described almost everything here, but if you see with respect to gear, they are not very important, but I want to give you a feel about internal energy. You need to understand internal energy and you need to feel it. So then what we need to do here, listen, if you consider molecules which is present in the system, okay, suppose, let me erase it. Okay, listen, this is my system. As a whole, it is not going to change much. Either the distance is not going to change or the velocity as a whole of the system is not going to change. So microscopically, change in kinetic energy and change in potential energy will be negligible. But internal energy, which is nothing but n number of molecules will be there, right? There will be n number of molecules in the system. If you see it microscopically, I could have n number of molecules. And the motion of that particular molecule, due to that motion of that particular molecule, the energy which is possessed due to that motion is going to be internal energy. So to be precise, internal energy completely depends on the degree of molecular activity. Okay, if there was more molecular activity, then internal energy is going to be more. If molecular activity was less, internal energy will be less. So first, what is internal energy? Any form of energy which is associated with molecule. Any form of energy which is associated with molecule, it is internal energy. If there is more degree of molecular activity, if more molecular activity was there, then internal energy is going to be more. Now, why I used the word any? Any form of an energy associated with molecule? Because there are different forms of energy associated with molecule. I am just going to give you a glimpse. The first is molecular translation. Molecule can just translate. Okay, so each molecules can easily translate over, right? It can just easily move over. Okay, it can just move over inside the system. Molecular rotation, in case of polyatomic molecules, okay, so two molecules which are attached, it can rotate. Okay, it can rotate. So molecular rotation. And then if you think about electrons, okay, so electrons are going to rotate over the electrons are going to rotate over the center nucleus, right? And this molecular translation, like for example, think about this. This molecule is going to have some velocity, right? And due to that velocity, this molecule is going to have some kinetic energy. Okay, that kinetic energy will be included in this internal energy. Listen carefully, listen carefully, listen carefully. This kinetic energy is macroscopic form of kinetic energy, which means I am considering total body. Okay, as a whole, I am measuring kinetic energy. If I measure kinetic energy for a single molecule, then it will included in internal energy. So kinetic energy associated with single molecule. Okay, kinetic energy associated with molecules has to be taken in internal energy. Now similarly, if suppose a body rotates, okay, total body rotates, then there will be rotational kinetic energy, as we know already. Okay, there will be rotational kinetic energy. If a molecule rotates, again there will be rotational kinetic energy, and that rotational kinetic energy of molecule should be taken as internal energy. Okay, that's what I am saying. Sum of all the energies associated with molecules. So all the energies associated with the molecules has to be taken as internal energy. Now next, similarly, electrons are rotating the nucleus. It is nothing but a form of rotational kinetic energy, and here it is molecular form, okay, microscopic form. So that has to be included in internal energy. Molecular vibration, due to vibration there is going to be some form of kinetic energy, right? Sorry, potential energy. Okay, so that will also be, that is molecular form again it is a microscopic form. That has to be included in internal energy. Electrons, when it is moving along its axis, it will spin. Okay, so electrons will spin along its axis, basic chemistry which you would have studied in your 11th or 12th. Okay, so that motion of electron, the spinning of electron will result in some energy, and that energy is to be included in internal energy. All these forms are some kind of motion, right? Due to some kind of motion of a molecule, either rotation or translation or vibration. It corresponds to some kind of motion, and the energies of molecules, okay, the energies of molecule, which is corresponding to some kind of motion or some with respect to kinetic, I can say that it is a kinetic energy. Okay, so kinetic energies, either it is rotational, vibration, rotation or translation or spinning, some form of motion of molecules in a molecular level. All those combinedly called as sensible energies. Okay, and this sensible energy is also one form of internal energy. Okay, now so this is the first classification which we are seeing. Okay, as I said, sum of all the molecular energies are internal energy. This is one. And what is that sensible? Sensible energies are nothing but the energies which is associated with motion of the molecule, maybe vibration, maybe rotation, maybe translation, or whatever it is. Okay, now second, we will go for one more thing. Just think about gases, liquids and solids. Okay, so in case of solids, the force of binding between molecules will be very high compared to liquids. It will have somewhat less. Compared to gases further less. So we know this from basic science. So solids are going to have a strong bondings between the molecules, and then liquids, then gases, which means in solids the molecules will have some restriction in the motion. Okay, so which clearly means the energy which is possessed due to motion of the molecule in solids will be less. It will be more in liquid, it will be further more in gas, which is clearly states internal energy of gases are going to be always greater than that of liquids, which is going to be always greater than that of solids. Why? Because molecular activity will be less in solids because of the strong forces. Okay, and in liquids it will be somewhat less than solid, and in gases it will be further less. Okay, so in gases internal energy will be more. Okay, now next form of energy which I am going to discuss is latent energy. If suppose I am supplying some heat, okay, when it is under liquid form, the molecule starts to break and the liquid form will get converted into gases, and that is nothing but phase change. And during the phase change, the energy, the molecular form of energy which is associated during the phase change, that is latent energy. We will talk about this latent energy again, okay, further when we are discussing about pure substances, latent heat, sensible heat. We'll talk about that later. So simply now, the energy of the molecule, which is associated with the phase change, it is latent energy. When it will happen? If suppose I am supplying some heat, the liquid is getting converted into gas due to the breakage of the bonding forces. So it is majorly due to the breakage of this molecular binding forces. Now chemical energy, what is this chemical energy? If you consider an atom, okay, so in an atom, nucleus will be there, proton will be there, neutron will be there, electron will be there, and the bonding, okay, the atomic bonding inside the atom. So it is not a molecular bonding, it is atomic bonding inside the atom. The energy which is possessed due to that atomic bonding is chemical energy. Okay, so that is chemical energy, that I am going to give it as 3, latent energy is 2. Okay, now finally nuclear energy, that is due to the energies which is associated with nucleus itself, okay, nuclear bonding. Especially that nuclear energy will be more more predominant in that fusion and fission reactions, which we are not going to study in thermodynamics. Okay, in our thermodynamics, it's completely chemistry. Okay, so all this microscopic or molecular level energies summed up will be internal energy. That's it. I hope you would understood that what is that internal energy in a detailed manner, right? So internal energy is nothing but sum of all the molecular form of energies. Either it is molecular form of kinetic energies, that is with respect to motion, or with respect to phase change, or with respect to the bondings inside the atom, or with respect to bonding inside the nucleus. Everything combinedly internal energy. Now one point which you would have already observed it. Here I am supplying heat and the liquid is changing to gas. Okay, why it is actually happening? Because I am increasing the temperature. It's pretty much evident that if I increase the temperature, okay, see, I will say it in this manner. I will say in the reverse manner, in the normal manner. See, we know that internal energy depends on molecular activity, which means how much the molecular activity is happening and what is the velocity of the molecule. Okay, velocity of the molecule with which it is traveling. What I need to do to increase the velocity of the molecule, or what I need to do to increase the activity of the molecule? Very simple. Increase the temperature. Increase the temperature. We know this again from basic chemistry. Okay. So if I increase the temperature, the molecular activity is going to increase, which indeed means that internal energy is going to increase. So internal energy is direct function of temperature, which I already said to you, okay, when I was discussing specific heat, but I didn't given you the reason. Now you got the reason why. Internal energy depends completely on molecular activity. For increasing molecular activity, I need to increase the temperature. So if I have more temperature, if the system is at higher temperature, then it's going to have higher internal energy. As simple as that. Okay, now, so this is our total energy, right? So what will be change in energy, change in total energy, change in total stored form of energy? It's going to be change in kinetic energy plus change in potential energy plus change in internal energy. And we know as I discussed already, for a closed system, okay, dKE and dPE, which means change in potential energy and change in kinetic energy are negligible. So this will be 0, this will be 0, changes are becoming 0. So dE is going to be finally, that is change in energy, is going to be finally change in internal energy. So now what happens to our first law of thermodynamics for a process? D dash Q is going to be equal to D dash W plus DE, and we got DE is equal to DU. So D dash, first, this is our basic form, okay, this is our basic form, and there is no assumption here, which means it can be applied to both reversible and irreversible process. Okay, first law of TD for a process. Let me include this assumption to it. Okay, so if I make it like that, what will happen? D dash Q will be equal to D dash W plus DU. Okay. So what are the assumptions here? Again, this is also can be applied to both reversible and irreversible process. Okay, because I didn't introduce any other things which is going to change the reversibility or irreversibility. But what is the next assumption? Kinetic energy and potential energy changes are neglected. Okay, so just adjust with my handwriting. Okay, right. So kinetic energy changes and potential energy changes are neglected. Now, if suppose, listen, is equal to PdV plus du. What is this? What are the assumptions included in this equation? First, in place of d dash w, I substituted PdV. So only reversible process. Only reversible process. And then I replaced dE with du, which means kinetic energy and potential energy changes are neglected. Of course, it is for a closed system. Okay, so don't expect me to write closed system for each and every statement, because open system we will discuss separately. Okay, that is a steady flow and unsteady flow equation. So this or the three forms. Okay, still we can write one more form if you want to. Okay, which I already given. What are the assumptions here? Only one assumption: reversible process and of course closed system. Okay, all the equations are applicable for closed system. Okay, but this first equation is applicable for both reversible and irreversible. Second, reversible, irreversible, kinetic energy, potential energy changes are neglected. Third, only reversible, kinetic energy, potential energy changes are neglected. Fourth, reversible only. That is, I am not neglecting that changes in kinetic energy and potential energy. Very, 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 very important.